Hello. In the second part of Bohr atom model, we are discussing the origin of hydrogen spectrum. Hydrogen atom contains only one electron, but its spectrum consists of a large number of lines. Bohr supplied the reason. A given sample of hydrogen contains a very large number of atoms. Suppose energy is supplied to this sample of gas. Different atoms will absorb different amount of energy. The one electron in different atoms will therefore shift to different energy levels depending on the energy absorbed by the atoms. This is the spectra of a sample of hydrogen gas. Some of hydrogen atoms may absorb sufficient energy to shift their electrons to the second energy level, while some others may absorb more energy and may be able to shift their electrons to third or even to one of the higher energy levels. The electrons then tend to fall back almost immediately to one or other of the lower energy levels. The various possibilities by which the electrons fall back from various excited energy levels to lower energy levels, called electronic transitions, are depicted in this picture. During each transition, energy is released, which appears in the form of radiation of specific frequency and hence of specific wavelength. Suppose an electron lying in energy level N2 with energy E2 jumps to a lower energy level N1 with energy E1. Then the difference in energy delta E will be E2 minus E1, and from the equation of energy of electrons in hydrogen atom, we have the expression of energy of electron in the hydrogen atom, and for E2 this will be the equation, since here n is equal to 2 and for E1 it's n1. The difference in energy would be emitted in the form of radiation of a specific frequency. The emission spectrum of hydrogen would thus show a line at the frequency of emitted radiation. If nu is the frequency of the spectral line, then nu equal to delta E by H, and substituting delta E, we will have the equation for the frequency as this. Since these terms are the common factor, we are taking it in outside, and in brackets we have only 1 by n1 square minus 1 by n2 square. We know the frequency equal to velocity of light by lambda, which is c into 1 by lambda, where 1 by lambda is nu bar, is the wave number. It is the reciprocal of wavelength. Always in spectral transitions we are representing the spectra in wave numbers, not in frequency. So the equation of nu bar become nu by c, and the new equation in terms of wave number will be nu bar equal to 2 pi square z square m e raised to 4 by 4 pi epsilon 0 square c h cube into 1 by n1 square minus 1 by n2 square, where Nu bar is the wave number. As I already said, it is the reciprocal of wavelength in meters. E is the charge in coulombs. M is the mass in kilogram. H is the Planck's constant in joule seconds. And C is the velocity of light in meter per second. This quantity is called Rydberg constant and its value is 1,09,678. The appearance of various series of spectral lines in the emission spectra of hydrogen can be explained with the help of this equation. The first series, Lyman series, are produced when the electron jumps from second, third, fourth or a higher energy level to the first energy level. The frequencies of various spectral lines of this series can thus be obtained by substituting N1 is equal to 1 and N2 is equal to 2, 3, 4, etc. in this equation. Next, the Bohr series results when the electron jumps from third, fourth, fifth or higher energy levels to the second energy level. The frequencies of various spectral lines of the Bohr series are obtained from the same equation by substituting N1 is equal to 2 and N2 equal to 3, 4, 5, 6, etc. In the same way, the Paschen series originate from the electronic jumps from the 4th, 5th, 6th, etc. energy levels to the third energy levels, and the frequencies obtained by substituting N1 is equal to 3 and N2 is equal to 4, 5, 6, etc. and so on. The frequencies of the spectral lines of the three series calculated by using this equation are determined experimentally, and the agreement between the experimental and the calculated values were very excellent. This offered a very strong support to Bohr theory of the hydrogen atom. Although Bohr theory could explain the emission spectra including fine structure of hydrogen atom, this model could not explain a number of significant observations. The main shortcomings of Bohr theory are: Bohr theory fails to explain the spectra of multi-electron atoms. Bohr atomic model fails to account for the effect of magnetic field on the spectra of atoms or ions. It is observed that when the source of a spectrum is placed in a strong magnetic field, each spectral line is further split into a number of lines. This is called Zeeman effect, which cannot be explained on the basis of Bohr model. In 1923, de Broglie suggested that electron-like light has a dual character. It has particle as well as wave character. Bohr theory treats electron only as a particle. Another objection to Bohr theory comes from Heisenberg's uncertainty principle. According to this principle, it is impossible to determine simultaneously the exact position and momentum of a small moving particle like an electron. The postulate of Bohr that electrons revolve in well-defined orbits with well-defined velocities is thus not acceptable. These are the failures of Bohr atom model. In the next lecture, we shall discuss de Broglie's concept and Heisenberg's uncertainty principle in some details, since these two concepts are mainly responsible for exposing the most serious shortcomings of Bohr theory. Thank you.